Right. Recording has started, so you can start the zone. Good luck. You can continue the presentation.
Okay, sir. Thank you very much. Uh, Let us give a
Excuse me,
minute until
Yeah.
my friend share his
sir.
slide.
Excuse me, sir.
Yes.
Can you give the access for to the share the screen?
All right. Hold on. Hold on. I'll give the access. I'll give access. Right. Please check now. Please check now.
Thank you, sir. Can
All right. Nice. Yeah, that's one. You can continue. Sorry for the disturbance.
Okay, it's okay, sir. All right, guys. Good afternoon, everyone. So thank you for joining us today. So let's explore the world of random access machines or RAMs. In this presentation, we will talk about the fundamentals of RAMs, their role in computer science, and how they help us analyze the efficiency and complexity of algorithms. So let's talk about what are the content in our presentation. Next slide. Okay. As you can see in this slide, we can see number 1 as overview RAM, number 2 as memory model, number 3 as RAM operations, number 4 program structure, number 5 time complexity analysis, number 6 practical applications of RAM, number 7 importance of RAM analysis, number 8 RAM algorithms, number 9 future directions and research, and finally question and answers if you are willing to ask from us. Okay, let's move into the next slide. Okay, random access machines. So what are exactly random access machines? RAMs are abstract computational models that represent simplified computer architectures. They are theoretical framework used in computer science to analyze the efficiency and complexity of algorithms. So let's talk about some key features about random access machines. Next slide. Okay, key features of random access machines. As you can see in this slide, we can see memory, registers, program counter, instructions, simple instruction set, sequential execution, assembly-like language, computational power. Let's talk about these components in brief. So when it comes to memory, the first key feature of RAM. RAMs have a memory component that consists of an array of cells. These cells store values such as integers and serve as a storage medium for both program instruction and data. The memory allows the program to access and manipulate specific cells using the unique address. So let's talk about registers in next slide. So when it comes to registers, it's another feature of RAM. Registers are small, high-speed storage units located within the RAM. They hold data that is frequently accessed or currently being processed. Registers help in improving the performance and efficiency of the RAM by reducing the need to access memory repeatedly. So let's talk about program. What is program counter in next slide? Program counter. When it comes to program counter, it's a special register in the RAM that keeps track of the address of the next instruction to be fetched and executed. It ensures the sequential execution of program instructions by incrementing automatically after each instruction is executed. So that's all about program counter, and we can talk about instruction in next slide. Okay, instructions. What are instructions? RAMs operate on a set of instructions. These instructions represent the operation for tasks that RAM can perform. Each instruction is represented by a unique binary code and specifies a particular operation such as arithmetic, logic, or data manipulation. So I would like to hand over this presentation to Mr. Savin.
All right. Thank you, Dasun. So guys, as Dasun brought you guys into an introduction and a quick overview about random access machines, I would like to get you into the execution process of random access machines. So now we all have to know that random access machines are computational models that allow us to analyze algorithms and understand their efficiency. And another special thing you must know is why and what's the importance of understanding the execution process. All right, guys, if we move on to the next slide, we can see the significance, we can see the significance of execution process by a few points. Since these are very big topics, I'm going to just present you the points to you quickly, and then you can do your own research on this afterwards. So first, what's the significance of understanding execution process? First point, it will provide us insight into computer architecture. And the second, it will enable us to build programs efficiently. And it helps us on debugging and troubleshooting. And also, finally, it helps us to optimize our performances. So guys, without wasting any time, let's straight dive into the steps involved in executing instruction in a RAM to understand this part better. So let's go into the next slide. Okay, so yeah, execution. All right. Let's talk about execution process as a whole first. So as you can see in the slide, during computation, the components of RAM work together in a coordinated manner to execute instructions and manipulate data. That's what we call as execution process as a whole. So let's move to the next slide. And guys, the execution process mainly consists of three main steps, which are fetch, decode, and execute. Since this is a very long story short, now let's talk about each component separately. So let's move to the next slide. So first and foremost, we must understand the fetching process, since it's the first step of the execution process. The fetching process is a fundamental step in the execution of instructions by a computer system. It involves retrieving the next instruction to be executed from memory, making it available for further processing by the CPU. So guys, we must know that program counter, or we also call as PC, is used to determine the address of the next instruction to be fetched from memory. The PC is also incremented to point to the next instruction in line. So let's move to the next slide. Yeah, decode. Okay. So guys, we have already done the fetching. Okay. So after fetching the instruction, we move on to the decode step. Here, the fetched instruction is decoded to determine the operation to be performed and the operands involved. We identify the instructions of code which specifies the type of operation to be executed. Next slide. So we have now done the fetching and the decode. Now we have execute. So now we proceed the execute step. Now, based on the decoded instruction, the RAM performs specified operation using the provided operands. This execution can involve accessing memory locations, performing arithmetic, logical operations on registers, or modifying control flow. And the last slide of the execution process, which we talks about update and repeat. After the execution of an instruction, the RAM may update the registers, memory, and program count as necessary. It then repeats the fetch, decode, execute cycle, moving on to the next instruction indicated by the program counter. So guys, in brief, the execution process in a RAM involves the steps fetch, decode, and execute. It starts with fetching the next instruction, decoding it to identify the operation, and executing the operation using specified operands. The RAM then updates its state and repeats the cycle for subsequent instructions. By understanding this process, we can analyze the efficiency and performance of algorithms implemented on RAMs. This knowledge helps us to make informed design choices and optimize our algorithms for better computational results. So guys, that's all about the execution process we have to talk about when we're studying about random access machines. And now I would like to hand over the presentation to Dinusha to talk about the next part of our presentation.
Thank you, Savin. Now let's dive into the slide. I will discuss some fundamental instructions that are at the heart of how computer works. As you can see on this slide, this instruction include the load instruction, store instruction, and some of arithmetic instruction like add instruction and the subtract instruction. Let's explore what are these instructions. Okay, let's start with the load instruction. Imagine computer memory as a giant warehouse filled with countless storage spaces. The load instruction is like a magical forklift that can retrieve data from a specific storage space and bring it to the working area of the computer, which we call the registers. It's like grabbing a specific item from a shelf and placing it on your desk for easy access. Now, let's move to the store instruction. In this, it's just like the load instruction brought data to the register. The store instruction allows us to take data from the register and storing back in the memory. It's like tidying up your workspace and placing an item back on the shelf when you no longer need it. So the store instruction ensures that the valuable data is safely stored for later use. Now, let's move to the next slide. In this slide, we are discussing about the arithmetic instructions. The add instruction enables us to perform addition, just like we do in mathematics. We can select two values, such as numbers or variables, and the computer will add them together, providing the result in the register. It's like having a virtual calculator that can effortlessly add numbers for us. Lastly, we have the subtract instruction. Just as the name suggests, the instruction allows us to subtract one value from another. We choose two values, and the computer performs the subtraction operation, providing the result in the register. It's like having a digital math wizard that can subtract numbers at lightning speed. Now let's shift our attention to what are the RAM programs. Okay, let's begin with the very essence of RAM programming. The RAM programming involves using an assembly-like language, a language that allows us to communicate directly with the computer's memory. Through this language, we can manipulate data and control the flow of the execution. In RAM programming, we use instruction as our building blocks, much like the letters of an alphabet. These instructions are precise commands that tells the computer to what to do. We can perform operations such as loading data into registers, storing data back into memory, and manipulating values using arithmetic operations. With these instructions, we sculpt the behavior of our programs. Okay, now let's dive into this slide. So guys, in this slide, we are talking about the RAM complexity analysis. So guys, imagine you have two algorithms to solve the same problem. Complexity analysis helps us to understand which algorithm is more efficient and how its performance scales with the input. It's like comparing two routes to reach a destination. One might be short and faster, while the other could be long and slow. In complexity analysis, we use mathematical models to quantify the efficiency of algorithms. We examine factors such as the numbers of operations performed, the memory utilized, and the time it takes for an algorithm to run. By understanding these factors, we gain insight into how algorithms behave as we increase the size of the input. Why the RAM complexity analysis is important? So, complexity analysis helps us to make informed decisions when designing algorithms. We want to create algorithms that can handle large data set efficiently, minimizing time and resources. Complexity analyzing guides us to choosing the best algorithm for a given problem and ensuring the optimal performance. Complexity analysis also allows us to understand the limitations of the algorithms. So some problems are inherently complex and require significant time and resource to solve. Complexity analysis help us to identify these limitations and enable us to make trade-offs between time, memory usage, and the accuracy. Okay, then we will move to the time complexity. So the time complexity is all about measuring the time or number of computational steps an algorithm takes to solve a problem. It's like tracking the time it takes to complete a task or counting the steps you need to climb the staircase. And why is time complexity is important? So this helps us to evaluate the efficiency of algorithms and make informed decisions. And we want to choose algorithms that can handle larger problems without slowing down significantly. The time complexity guides us to selecting the most efficient algorithm for the task at the hand. So we will move to the space complexity. The space complexity measures the amount of memory or space an algorithm requires to solve a problem on a RAM machine. When we analyzing the algorithms, we want to understand how their memory usage change as the problem's complexity increases. We aim to predict how much memory and algorithms will require to handle larger problem sizes. It's like estimating how much space a puzzle with more pieces will occupy on the table. And what are the importance of this space complexity? So the space complexity guides us in selecting the most efficient algorithm for managing the memory. And we want to choose algorithms that can handle larger data sets without consuming excessive memories. Oh, then after that, I would like to hand over the presentation to Dasun.
Okay, thank you, Dinusha. So RAM versus real computers. What is this? Okay, let's discuss about it. What is the differences between RAM models and real computers? Let's start with RAM model. RAM models provide an abstraction of the idealized random access machine. They simplify computational analysis by offering a straightforward memory structure, simple instruction sets, and sequential execution. RAM models serve as a foundation for theoretical analysis, allowing us to understand fundamental concepts and algorithms. However, it's important to note that real computers go beyond these models. Let's talk about real computers. When it comes to real computers, it's an additional complexity beyond RAM models. They incorporate hardware features such as cache hierarchy and pipelining to improve performance. Moreover, real computers operate under real-world constraints. Factors like disk I/O, network latency, and parallel processing can significantly impact algorithm efficiency. It's crucial to consider these complexities and constraints when designing algorithms for real-world computing systems. Understanding the differences between RAM models and real computers help us develop more efficient and practical solutions. So when it comes to RAM versus real computers, we can finally say that RAM models provide a simplified abstraction for theoretical analysis, while real computers incorporate additional complexities in real-world constraints. By recognizing these differences, we can design algorithms that are better suited for real-world computing scenarios. So I would like to hand over this presentation to continue to Mr. Savi.
Thank you, Dasun. So now let's explore some fundamental algorithms for searching and sorting. These algorithms actually play a crucial role in computer science and are essential for solving a wide range of problems efficiently. Let's dive into our first algorithm, which is linear search. So let's move on to the slide. Okay. Actually, guys, linear search is a simple algorithm used to find a specific element within an array. Does anyone have any idea about it? I guess not. So, okay, I'll tell a story. So, think we have a box full of toys and we have to find a car. Okay. So, a linear search is like going through each toy one by one, starting from the top of the box. Okay. You pick up each toy and see if it's the toy car you are looking for. Okay. If it is, you stop searching and say, I found it. But if it's not, you keep going until you either find the toy car or reach the end of the box. So basically, it works by iterating through each element of the array and comparing it with the target element until a match is found or the end of the array is reached. And next we have binary search. Okay. Binary search is which is a more efficient search algorithm suitable for sorted arrays. Okay. It follows a divide and conquer approach. It starts by comparing the target elements with the middle element of the array. If they match, the search is successful. If the target is small, the search continues in the lower half of the array. Otherwise, it continues in the upper half. The process is repeated until the element is found or the search space is exhausted. Now let's move on to the sorting algorithms, starting with the bubble sort. Bubble sort is a simple comparison-based sorting algorithm. It repeatedly compares adjacent elements in the array and swaps them if they are in the wrong order. This process is repeated until the entire array is sorted. So guys, in brief, we have explored three important algorithms, which are linear search, binary search, and bubble sort. Linear search is suitable for unsorted arrays, while binary search is efficient for sorted arrays. Bubble sort, although simple, may not be the most efficient sorting algorithm for large datasets. Understanding the time complexities of these algorithms helps us choose the right approach for solving specific problems efficiently. So I will hand over the presentation to Dasun to talk about the next one.
All right. Thank you, Savin. Let's talk about practical applications of RAM or random access machines. I would like to discuss the practical applications of random access machines. So RAM models are not only valuable for theoretical analysis, but also find numerous practical applications in various domains. Okay, let's explore some of these applications. So let's move to the next slide. Optimization problems. What is optimization problems? RAM models are useful for analyzing the time and space complexities of algorithms used in optimization problems. For example, algorithms for solving linear programming and integer programming can be evaluated and optimized using RAM complexity analysis. So let's talk about cryptography in next slide. Cryptography. When it comes to cryptography, RAM models are valuable in analyzing the complexity of algorithms using cryptographic systems. Cryptographic algorithms such as encryption, decryption, digital signatures, and secure hash functions can be evaluated and assessed using RAM complexity analysis. So let's talk about machine learning and data analysis in next slide. Machine learning and data analysis. What is this? RAM complexity analysis is relevant in studying the performance of algorithms using machine learning and data analysis tasks. This includes algorithms for clustering, classification, regression, dimensional reduction, and pattern recognition. So I would like to hand over this presentation to Sudhirusha to continue.
Thank you, Dasun. And I would like to discuss the exciting future direction and ongoing research in random access memory. As computing evolves, researchers are exploring the avenues to enhance the capability and efficiency of RAM. Let's explore the researches of parallel and distributed RAM. The first area of research focuses on extending the RAM model to parallel and distributed computing environments. As computational demands increase, parallel processing and distributed systems offer opportunities for enhanced performance. And I will move to the next slide. In this, we are talking about the approximation algorithms. The second area of the researchers involves the development of the approximation algorithms within the RAM framework. As computational problems become increasingly complex, finding exact solutions may be computationally infeasible or time-consuming. In these algorithms offer an alternative approach. These algorithms provide near optimal solutions that are sufficiently accurate for practical purposes while reducing the time and space complexities involved. Researchers are actively exploring and designing approximation algorithms within the RAM model to address real-world challenges. Now I would like to hand over this presentation to Savin.
Uh, Thank you, Dinusha. So guys, now I'm going to get you through two fascinating areas that future directions of RAM can go. Which first is quantum RAM and the second is algorithmic game theory. These fields represent exciting frontiers in the world of computing, offering new insights and possibilities. Let's begin with quantum RAM. So guys, I think most of you guys have heard about quantum computing's growth over past few years. As quantum computing continues to advance, researchers are exploring RAM-like models specifically designed for quantum computers. Quantum RAM or QRAM aims to provide efficient and scalable memory access in quantum systems. It allows for the storage and retrieval of quantum information using quantum states, enabling more powerful computations and potential breakthroughs in various domains. So next slide. Then there's a really cool field called algorithmic game theory that combines games and problem solving. It's like mixing the rules of games with the power of computers. Let's imagine you and your friends are playing a game together. In algorithmic game theory, we study how people make decisions in games when they want to win. We use fancy math and computer science to understand how they think and what choices they should make. Algorithmic game theory helps us understand these strategic interactions between players and how their choices influence the overall outcome of the game. Now let's talk about two potentials of these two areas. Quantum RAM holds tremendous potential for applications in cryptography, optimization, machine learning, and simulating quantum systems. It can accelerate complex computations, enhance data storage capabilities, and revolutionize our approach to solving computational problems. The development of efficient RAM models is crucial for realizing the full potential of quantum computing. And algorithmic game theory finds applications in diverse fields, including online marketplace, social networks, resource allocation, and mechanism design. It helps us analyze strategic decision making in these contexts and design efficient algorithms that promote desirable outcomes. By understanding the dynamics of strategic interactions, we can devise algorithms that balance individual incentives and overall system objectives. In brief, quantum RAM and algorithm game theory represent fascinating areas of research at the forefront of computer science. Quantum RAM offers promising advancements in quantum computing and memory access, while algorithmic game theory provides insights into strategic decision-making in computational environments. Both fields have the potential to transform various domains and drive innovation in the coming years. So that's all on my part of the presentation, guys, and I would like to hand over the presentation to Dasun to end our presentation. Thank you.
Okay, Stavin. So this is the end of our presentation about random access machines. So if you guys got any doubts, you can ask from us. Feel free to ask. Any questions?
All right, that's one. I think there's no questions from the audience. All good. Thank you. Very nice presentation.
Okay, sir. Thank you very much, sir.
Right, guys, a few updates that thanks. Yeah, everyone from the team, Savin and all the team members. Good job, actually. Give a big clap, everyone. No need to keep keep it quiet. Good. Right. So good. Yeah. Any questions? No. Good. Right. All good. So actually, I have done a minor modification for your assessments, which is 20% for the presentation, and last assessment was cancelled because of the very good performance from all students. So we have removed it. The second thing that I want to tell you is I have shared 2 links with your representatives. One is a Telegram group. The other one is the attendance sheet. Could you please check whether you have access to these 2 or not?
Yes, sir.
All right. Good. Right. So the people who wants to access to this Telegram, please keep it there, because what I'm doing is I'm sharing all the questions and the links in the Telegram group. So the people who are not in the Telegram group, please representatives, make sure to share the link, the assessment, the in-class activities, whatever we are doing. Please share with your Telegram group or whatever the method that you have to what we call this communication mechanism, right? I'm just sharing everything in the Telegram group. So if you are not in the Telegram group, no worries at all. Your representatives will share with you. This is the option that I can go through. This is the option that I have used in last COVID period. The online situations, that's how I manage the story. Right. Any other questions, guys, you have? Any other things to clarify? The other thing is I want all the PowerPoint presentations up to now, where the students are completed actually. I need the finalized or the presented presentation slides that you have, either PPT slides or what we call this PDF files. Could you please share it today itself? Then I can upload it to the what we call your course page, not the model. What is the it's model, right? I can upload it to your course page. So then it might be much convenient for everyone, and I'm planning to update the course page within this week, so you can have all the information until the end of this semester. Because it's partially developed at the moment. So I'm planning to complete it this week. So your support is very important, so I can update the course page accordingly. I have some of I have all the slides actually, not some, but some of modifications that I have proposed to most of the groups. So after the modification, some of the teams send, some of the teams not. Whether you send it to or not, please make sure to share it with me today itself. Then tomorrow morning I can complete this what we call this course page completion work, entire things that the objectives and whatever the courses, the materials, and whatever the things that we have to complete within this semester. So we have only a limited time remaining. So we have to complete all of these things. All right. And I would encourage to whatever the in-class activities not to share with any other student who do not attend, because this is in-class activity. The people who are not attending, please don't share with them. I don't like to have that kind of a thing, and I like to have in-class engagements as it is. That means the people who are attending to the class should do, not the others. So please don't share with your other colleagues. I have 2 options. One is I can take the attendance from these teams. Just go to and download the attendance. It's not a big deal, but it's much easy to keep you eye on the things what happens in here and there. Right. Any other questions, guys? All good? No questions? All right. If you don't have any questions, this team shared a set of questions, simple set of questions with me to ask from you. So I have shared the forms link with you. You have 5 minutes of time to complete. I don't think it takes 5 minutes, but I will give around 5 minutes maximum to complete this activity. Representatives, please make sure to share with all the colleagues in your group. I have shared already in the Telegram group. Any questions? Let me know. I'll wait 5 minutes, then we'll go to the next Teams presentation. You have 30 seconds remaining, guys. Make sure to submit within these 30 seconds. So please submit, guys. Please complete your submissions now. I'm going to stop the acceptance of these responses. So please complete it. I will wait another 15 seconds, Sarah. Right. All right. We'll go to the next presentation group. I have stopped the response acceptance. So we'll go to the next team. Who is the next team that planning to do the presentation?
So it's us.
All right.
So can we have the screen share access?
Yeah, I have given access for everyone.
Okay, Nilasi, you can share the screen. So good evening, everyone. I know this is not our usual setup for the class, but we are not. It's not like we're not used to this. The only thing that's different is the sickness that is spreading. So our presentation today is about lambda calculus. I'm pretty sure most of us here hasn't heard about lambda calculus. And we put up a presentation to give you a small idea about what lambda calculus is. So next slide. So this is a small overview of what we will be discussing today. So I will pass the I will pass the chance to Ravindu to start with history of lambda calculus.
Thank you, Tanudha. To start off, lambda calculus was invented by Alonzo Church, a mathematician at Princeton University in United States. His main interest was in the notion of a function from a computational perspective, and the answer to his question is lambda calculus. Over to you, Tanudha.
So a fun fact, Alonzo Church was actually a PhD supervisor for a very famous person in the computer science field. So can anybody guess who it is? It's actually, I'll give you all a small hint. He was actually the father of modern science, computer science. Can anybody guess?
Alan Turing.
Yes, Mihan, Alan Turing. As we know, Alan Turing invented the Turing machine. Turing machine captured the basic state-based model of computation, and his PhD supervisor, Church, was able to capture the basic functional notion of computation with his invention, lambda calculus. So Ramindu will continue on the Church's and Turing thesis.
Thank you, Tanudha. Ultimately, these two quite different notion on notions, one function and one state-based tuned on out of B equivalent. This is what is called the Church-Turing hypothesis. Church-Turing theory is a fundamental concept in computer science and the theory of computation. It states that any effectively calculable function can be computed by the Turing machine. Next, please. Lambda sign. The lambda sign, the character used to represent lambda abstraction in lambda calculus. It is a fundamental part of syntax in lambda calculus and functional programming language. The lambda sign is actually the 11th letter of Greek alphabet and has been used for century in the field of mathematics and physics. Over to you, Nilasi.
Yes, thank you, Ravindu. I would love to continue this as an interactive session, but as we all know, it would take all 4 hours waiting for someone to unmute and answer every time I ask a question. So please bear with me and pay attention because you might actually find it interesting and fun. Now, as we all know, lambda calculus is a significant factor in the field of computer science. It is super powerful and super flexible, but it looks like an alien language at the first glance, so won't get the best first impression. To make our alien language somewhat human, we will start with the main components, which are variables, lambda abstractions, and function applications. To start off with variables. These are used to represent inputs, outputs, and bound variables within lambda expressions. In the instance where we are introducing variables, we first write the lambda sign, Ravindu explained before, followed by the name of the input and a dot as shown in the given example. This is also called a parameter or formal argument. These are typically represented by single letters. Their dependency is based on their scope within the lambda abstractions, and during reduction or evaluation, these can be substituted with other values. Moving on to lambda abstractions. This is the process of creating an anonymous function by binding a variable with the lambda expression. This is denoted by lambda symbol followed by a variable, a period, and the expression representing the function body.
So Nilasi, what if we want to apply a function to more than one argument? What do we do?
Yes, Tanuda. Then we can use the technique called currying, which was invented by the American mathematician Haskell Curry. Currying is a method to transform a function that takes multiple arguments into a sequence of functions, each taking one argument. Currying can be utilized for partial application, function composition, and higher order functions. And explaining the third main component. Function application is the process of using a function by providing arguments and obtaining results. It involves invoking a function and passing the necessary values or expressions as inputs. Next, I will explain the conversions of lambda calculus. There are 3 main types of conversions or reductions, namely alpha conversion, beta reduction, and eta conversion. Alpha conversion is used to rename intermediate values in abstractions to avoid variable capture, whereas beta reduction is the application of a function to an argument, while eta reduction allows to introduce or eliminate a function abstraction. I will now hand over the presentation to Tanuda to continue with the calculations, which should be interesting part for you all as BA students.
Thank you, Nilasi. So we're going to learn about a little basics of the lambda calculus. And so, Nilasi, next slide. Nilasi. Thank you, Nilasi. So when it comes to lambda basics, what we need to, we will be learning from what is as a continuation of what Nilasi said. So for church, a function was a black box that you weren't allowed to look inside. So it takes an input, in this case, as you can see in the presentation, something like X. It's going to process it in some way and then produce a single output, which could be X plus 1 or X plus 2, whichever you would like. In the case of 2 variables, it's going to be, they're going to take 2 input variables and then process it in some way. As I told you, you are not allowed to look inside what look inside the black box, and then we can observe an output. So the two important things to remember in the function is that the black boxes, you cannot see the mechanics of what goes inside the box. All you can do is input some values and then observe the output. Second thing is that there is no internal state. They are pure. There is no hidden information we can use. This is actually quite different from the notion of computation that Turing was interested in with his Turing machines. In Turing machines, there was an internal state. So moving on to the next slide. So in this slide, we have explained how to actually define a function using lambda calculus. So the lambda sign, as Ramindu explained, is used to indicate the introduction of a function. So we're going to write the lambda sign, then the input variable, and then a period. As Nilasi actually explained this part. And then we have, then after the dot, what we explain is how the output is calculated in terms of the input. So when it's important to remember that if we have two input variables, we have to indicate the introduction of a function using the lambda sign for both of them, not for like one. So the so next slide. So we're going to do a small calculation. So bear with us while we do the calculation, and I'm going to share my screen. So we can't share the screen to annotate the thing. Okay, so can everybody see the screen? Can you see?
Yes, yes.
Okay, so we're going to, okay. So the question is, we're going to define a simple function that adds 2 to a number and apply to 3. So as I told you before, we are first going to we had to first write the function. So the parameter of the function would be x. And don't forget the dot. And then according to the question, the simple function should add 2 to the variable, right? So should be the output is calculated x plus 2. And so this is how we write the function. I will clearly write it for you. Just so it's lambda x dot x plus 2. This is the function that we write. And the question also goes on to say that it has to be applied to 3, right? So we have a parameter, which is x, and then we are going to apply 3 and substitute it to the argument. Okay? So we're going to write lambda x dot x plus 2, and we are going to substitute 3 for this. So we're going to substitute 3 here, which, like I told you, this is a very basic calculation. So the answer is going to be 5. So I hope everybody understood this simple calculation. So moving on, I'm going to show a little example of what you can do with it. We are going to move to the presentation. Nilasi. Let's see. Nilassi, you can share the screen.
Yeah, wait.
So this is the example we just did, and we have included it in presentation as a guide for you. So lambda calculus basically has nothing in it. It's just got variables, a way of building functions, and a way of applying the functions, right? So it doesn't have built-in data types or numbers or logical values or any recursions. So to perform these, you have to actually encode them. So the encoding we will show you, is the logical values true and false. So it's a question for the audience. So what do you use true and false in a programming language for? So, okay, since no one is answering, you use the true and false statement to actually make a choice, right? So if something is true, you say do one thing, and then if something is false, you say do another thing. So we are going to use this choice to actually encode the values. So as you can see on the screen, there is lambda x and lambda y, right? So it goes through the function, and then it makes a choice. So when it comes to true, lambda, and when we're encoding it, true is actually encoded. When we're encoding true, the output is always going to be the first choice. And when it comes to false, it's going to do the opposite and choose the second one. So we can't actually stop while encode, like after encoding true and false, we can't stop. So we have to actually use it in a logical operator and show you this actually works. So the logical operator we chose to show you was actually the not operator. It's actually the simplest logical operator that we chose. And the logical operator not is going to flip true to false and false to true, performing logical negation. So let's see if we assign not to true, whether we get false. Okay, so everybody remembers the syntax we just said for true and false, right? So I'm going to share the screen again. Okay, so the syntax we told for true was lambda x, lambda y, and it outputs the first choice, which is x. And then we got false, we got lambda x, lambda y, and then it outputs the second choice. So the logical operator we are going to use today is actually not. So first of all, we have to write a function for this, right? So we're going to write not equals lambda b dot b. This will be either one true or false. We're going to apply to false, and then we're going to apply to true. So if we write this function as a whole, it's going to be lambda b dot b and false and true. So this is what actually the output can be, right? It could be either false or it could be either true. This is actually the logical operator. And okay, so the valid definition for not is we are going to use is not true, right? So our input is going to be true, which in terms has to bring us false, right? So we define the function before is false, true, and our input is true. So again, this is the function. This part is the function. This is the input. So the function says that if if the function here says if I take inner B, apply to false and then true and true. So right now we're going to apply to true here. So instead of B, we can actually substitute true to it. So instead of this part, so we're going to write true, false, true. Because we are inputting true here. So we can actually substitute this part with true. Now, right now, true, false, true doesn't actually make any sense, right? So, but in lambda calculus, if we continue to expand this, we can actually get a proper idea of what it is. So if we, excuse me, so when we expand this true, as we know the syntax over here, it's going to be lambda x, lambda y, x, right? So given two inputs, it's going to choose the first one, right? So over here. Like these are the two things we have, false and true. So we input true and then we're going to get false because over here we chose x, right? Like the syntax. So that's how we actually use the NOT gate for the as in lambda calculus. I will pass the chance to Nilasi to continue on applications of lambda calculus.
Excuse me, guys. Thanks. It's a nice presentation up to now. So before the presentation, we'll do a quick question, guys, to keep you awake. So I have created a simple question. It's a small question related to the topic that we are discussing. Now I have shared the link with you in the chat. I'll give 2 minutes to respond to that question quickly. Sorry for the disturbance for the presenters. We'll see the answer for this question. I have shared it in the chat. I will give 2 minutes to give the answer. Yes, what's the question? Yeah, what's the question, please?
Say, so,
Yeah. Yes.
sorry, say it is mistakes.
Oh, all right. Nice. Still, you are raising your hand. You can take your hand down. You have 45 seconds remaining. All right, guys, please submit your answers. Time's up. Please submit your answers. Right. Sorry for the presentation, for the interruption for the presentation, guys. Continue. Thanks giving me time during your presentation. Yes, you can continue. Who is this? Rajini Balasuri, right?
Yes, sir. So thank you, sir. Lambda calculus is used in a world of computer science in numerous ways with various motives. Few of those applications are: it serves as a basic theory for many programming languages and influences when designing those languages. It is involved in artificial intelligence and natural language processing, plays a significant role when developing type systems and type theory. It helps in understanding the capabilities and limitations of computation while it is used in optimization techniques and program analysis. Now, I will explain some of the applications mentioned in detail. While lambda calculus is a theoretical construct, it has profoundly influenced the development of functional programming languages such as Haskell, Lisp, ML, and JavaScript, which leads us to pure functional programming languages. Now you must be wondering what these pure functional programming languages are and why they are so pure. These are the languages that strictly adhere to the principles of functional programming, and they are pure functions, immutable, and avoid side effects and have higher order functions. To further expand your knowledge on these languages, few differences between pure functional programming languages and traditional programming languages are: pure languages are immutable, which means that once a value is assigned, it cannot be changed. And in contrast, traditional languages allow variables to be modified during the execution of a program. Pure languages minimize or eliminate side effects, which are observable interactions with the external world beyond the return value of a function, while traditional languages often incorporate side effects as a fundamental part. In the world of artificial intelligence and natural language processing, lambda calculus is also widely being used. A few areas it has influenced are symbolic reasoning, automated theorem proving, functional programming in AI algorithms, time systems, and type interference. Ravindu will now explain type theory and plus points of learning our alien language.
Thank you, Nirasi. Type theory and lambda calculus. Lambda calculus is closely related to type theory and is often used as a foundation for formalizing and studying type system. Type theory provides rigorous framework for classifying and reasoning about types and their interaction within programming language or logical system. Lambda calculus, on the other hand, serve as a basis for defining function and evaluation expression. The combination of lambda calculus and type theory allows for the developing of type safe programming language and logical system. Next page. Studying lambda calculus offer numerous benefits and gains. Some of them are deeper understanding of computation, enhanced problem solving skill, functional programming proficiency, provide a strong theoretical foundation. Thank you. Over to you, Nirasi.
Yes, thank you, Ravindu. So to conclude our presentation, lambda calculus is highly utilized and highly beneficial in the digital world, especially in a world where digitalization is the future. We hope we gave you some idea about lambda calculus, that it is not an alien language anymore. We would be more than delighted to answer any of your questions with the knowledge we gained through our research. So any questions? So I hope there aren't any questions. Thank you for listening. Thank you, sir.
Thank you, sir.
Thank you, sir.
Continue the next one, guys. No need to wait. Continue the next one. I think you have another one, right?
you all can see the screen. Okay, good evening, everyone. So, as humans, we use various ways to solve our problems. But when it comes to computers, how do they solve their problems? So, what they really do is they look into real world solutions and try to implement a computer program to it. So, this computer implementation to solve problems are known as model of computation. So, today we are going to talk about one of those model of computations. I'm Vinisha and my teammates are Gihini and Nimasha, who is present in the meeting today. And we will be talking about finite state machines, a model of computation. So we will be going through each of these topics so y'all can get a better idea about finite state machines. So what is a finite state machine? A finite state machine or a finite automaton is a model of computation or a conceptual tool used to design systems. It is an abstract machine or a concept that can be in exactly one of finite number of states at a given time. These states can change from one to another in response to a set of inputs during a process called transition. Finite state machines, or in short FSM, depicts how a certain system processes a sequence of inputs that changes the state of the system. So in our previous presentations, some of our batchmates talked about other model of computations like Turing machines, recursive functions, and etc. But unlike those, finite state machines are a less complex model. Therefore, it is the simplest model of computation. Because of that, it has a very limited amount of memory, and therefore it performs very low-level calculations and computations. So this finite state machine concept is used in many real-life scenarios and many devices. For some of the examples are vending machines, turnstile gates, elevators, traffic lights, combination locks, and etc. So we will elaborate some of these in our later slides. So now that you can have a basic idea of FSM, let me say the basic idea or the summary of finite state machine. A finite state machine is a computing machine that has a fixed possible states, a set of possible inputs that can change the state, and a set of possible outputs. Also, there are various ways that we can represent a finite state machines. So let's look at an example to get an idea on the ways we can represent a finite state machine. Let's consider the operation of card-operated turnstile machine. So first, what is a turnstile? A turnstile machine is a gate with 3 rotating arms. You can mostly see in subways or amusement parks, which is used to control the access. So initially, the access is blocked, preventing anyone passing through. So once a card or coin is inserted, the machine will unlock and a single person can pass through the gate. After a single person passes through the gate will come back to the lock state because it will expect another person to insert a card or another coin. So it will be locked until another card is inserted or another coin is inserted. So this short video clip will show you the basic operation of a turnstile machine. Okay. So now we can get the basic main components in that turnstile machine. So there were 2 states, lock state and unlock state. And there are 2 possible inputs for a turnstile machine, which is swiping a card or maybe putting a coin and pushing through the arms. So what are the two states? Lock state and unlock state. What are the two possible inputs? Swiping a card or maybe pushing through the arms. So in between these states and inputs, there is some sort of a process. So this process is known as a transition. So in the turnstile gate, what is the transition happening in between? So let's take. In the lock state, no matter how many times the input push is given, there is no change in the state because the expected input in the lock state is swiping a card. So by swiping a card only, you can change the state from locked to unlocked. Likewise, in the unlock state, no matter how many times you swipe an additional card, it won't make any change because it's already unlocked. So to make a change in the state, what you have to do is you have to push through the arm. So the machine understands now the person who already swiped the card is trying to exit the gate. So I have to lock my state because I am expecting a new person. Therefore, the machine state will change from unlocked to locked. So y'all might not understand, like fully understand what I told up to now. So the basic thing we talked up to now, the finite state machine, there is a graphical representation for this finite state machine. So the graphical representation of finite state machine is state transition diagrams. So to talk about state transition diagrams, let's look at the main components first. So the first component is states. A state usually represented by a circle. It is the status of an algorithm. Only one state can be active at a time. And as I mentioned earlier, there are only a finite number of states. The second component is initial state. The initial state is usually represented by an arrow pointed at a circle. This is the starting point of the system. Next state is accepting state. Accepting state is also known as a goal state or a final state. It is usually drawn as double circles or a circle inside another circle. This is a subset of known states that whether the input we processed is valid or not. Our next component is transitions. A transition is usually represented by two states joined by a line. So transition is a set of actions to be executed when a condition is fulfilled or when an event is received. And our last component is alphabet. Alphabet is also referred as the language. It is the set of all valid inputs. Now that we understand all the components of a state transition diagram, let's look at the same example, but in the graphical representation way. So in the previous example, we had two possible states, the lock state and the unlock state. And I told you earlier, the initial state is represented by an arrow pointed at the circle. So the initial state in our turnstile gate is locked. Therefore, an arrow pointed at the circle is inside this lock state. So we have two possible states, the lock state and unlock state. And no matter how many times the push input is given at the lock state, there is no change because the expected input in the lock state is swiping a card. So pushing through the arms doesn't make any change. Therefore, it's a loop inside this lock state. But in the lock state, if you swipe a card, you can change the state from locked to unlocked. Likewise, in the unlock state, no matter how many times you swipe an extra card or you put an extra coin, it doesn't make any change there because the machine is already unlocked. Putting an extra coin it doesn't make any sense. But if you push through the turnstile gate in the unlock state, the machine understands the person who just swiped the card is trying to exit. Therefore, I have to lock the gate because I'm expecting a new person. Therefore, in the unlock state, when you push through the arms, the state will change from unlock to lock. So the same thing can be also represented in a state transition table. This is also very similar to a tree diagram. You have the current state, the possible inputs, the next possible state, and the set of outputs that can happen. So if I take one scenario, if the current state is locked and I swipe a card, and the next state would be unlocked, and the output would be the turnstile will unlock, and a single person can push through the arms. So it is valid. The same procedure is valid for all set of inputs. Okay, so to explain about the classifications of finite state machines, I would like to hand over the presentation to Imasha.
Thank you, Yunisha. Mainly, FSM is divided into FSM with output and FSM without outputs. FSM without outputs are classified again as deterministic finite automata and non-deterministic finite automata. When it comes to FSM with outputs, mini machine and Moore machine are considered as the main two types. Next slide. First, let's discuss about the deterministic finite automata, or in short DFA. DFA gets its name from the word determinism, which refers to the uniqueness of the computation. In DFA, there can only be one path for a specific input from current state to the next state. Next slide. This means in a DFA, given the current state, we know what is the next state will be. When the current state is being transitioned to the next state, there will be no choices or randomness. The relevant current state will have only one unique next state. Next slide. Now, let's see how a DFA is described. To define a DFA is a 5-element tuple consisting Q, sigma, delta, Q naught, and F. Q represented a finite set of states. Sigma represented the input alphabet. Delta represented a series of transition functions. Q naught represented the starting state, and F representing the setup of accepting state. Next slide. When defining DFA, it must be noted that there must be exactly one transition function for every input symbol in sigma from each state. Now I hand over to Gihini to continue with the presentation.
Thank you, Masha. So now we'll see how to draw a DFA. So now we have taken an example on a DFA that recognizes the language of all strings that end with a 1. So in this example, I have taken a language which I'll name as L1, and it says that this language consists of strings that end with a 1. So I'm assuming that this language has only binary inputs. Therefore, so this language will consist strings such as 1, 0, 1, 0, 0, 1, 1, 0, 1, etc. Now we'll design a DFA for this language. Next slide. Next slide, please. Okay. So first we'll start with our initial state. So for our initial state, I have named it as P. So to represent that this is the initial state, I have drawn a circle and an arrow pointing to it. Now we'll see what will happen when we get inputs such as 0 and 1. Next slide. So assume that I get the input of 1. So when I get the input of 1, I'm transitioning from state P to state Q. And to represent this transition, I have drawn an arrow between these two diagrams, so these two circles. So I have considered the Q as my final state.
Now, why did I consider Q as my final state? So in this example, it says that this DFA recognizes languages of all strings that end with a 1. So if I get a string that has only the digit of 1, or if that string ends with a 1, string should end up in the final state. So if a certain string ends up in the final state, that means that that certain string will be accepted. And if that string does not end up in the final state, the string will be not accepted by this DFA. So let's go to the next slide. Now imagine if I get a 0 as an input. So since the input is 0, it obviously cannot go to the final state. So because of that, it will loop back to the state P. Now, even after I reach the final state, I can still get several inputs. So let's go to the next slide. So assume that I get the input of 1. So when I get input 1, when I get the input 1, I will loop it back to the final state because all the strings should end in 1. And if I get a 0, I'm transitioning back to state P. So now that we have drawn this diagram, we will see the rest of the elements of this DFA. Next slide. So now we have our states P and Q, and then we have our input 0 and 1, and then we have our starting state as P and our final state or the accepting state as Q. So this table, which is represented by this lambda symbol, shows each possible state of this DFA. In addition to that, it also shows the transition between the current state to the next state based on the input given. So if I take an instance, if the current state is P and the input given is 1, it will transition to the next state of Q. So now I'm going to share my screen to show you guys another example. So we'll take a string. So can you guys see this board? Can you guys also see what I am drawing now?
Yeah, we can see.
Okay, thank you. So now I'm taking the string 1, 0, 1. So it's so now our starting state should be P, right? So now I'm giving the input 1. So now if I'm giving the input 1, it should go to state Q. And then our next input is 0. So when I get the input 0, I'm going back to the state P again. And for our last input, we have the input 1. So when we get the input 1, it goes again to state Q. So now earlier I mentioned that state Q is the final state. You can see that once it ends up in the final state, right? So because of that, we can say that this string will be accepted by this DFA. So Unisha, can you go to the next, please?
Now, other type of finite automata without outputs, which is called non-deterministic finite automata, in short, NDFA. NDFA gets its definition from the word non-determinism. This is because in NDFA, the exact state of the machine cannot be determined. Unlike in DFA, NDFA can have many paths for a specific input from current state to the next state. Go to next slide. I have mentioned earlier, a DFA that choosing a next state randomly is not possible. But in NDFA, the next state can be chosen randomly. All the next state may be chosen in parallel, which means multiple states can be chosen for the input. Next slide. Now, let's see how an NDFA is described. Just like DFA, NDFA also uses a 5-element tuple consisting of Q, sigma, delta, Q naught, and F. Q representing the finite set of states, sigma representing the input alphabet, delta representing a series of transition functions, Q naught representing the starting state, F representing the setup of the setting states. Next slide. When it comes to defining NDFA, as it is not necessary to have exactly one transition function for every input symbol in sigma. Because of this, NDFA can have multiple transition functions in the same state for the same symbol. Additionally, NDFA can use null transition function, which are indicated by the epsilon symbol. Null transition allow the machine to jump from the one state to the another state without having to read the symbol. Now, Gene will use an example to show you guys on how to apply the things we learned so far to describe NDFA.
Okay, now we will take an example on how to design a certain NFA. So our example, it says that we have to construct an NFA that recognizes strings that end in 1 in the third final position, which means that the one should be the third digit from the right, or that accepts the single. So now you guys can see that I have already drawn this diagram. So I will briefly explain what is going on in here. So you can see that the initial state of this diagram is A, and the rest of the states are B, C, D, E, and F. And we have the input 0, 1, and we also have a null input. So the final states are D and F. Next slide. So according to the logic of this diagram, this NFA can accept strings such as 111, 1100, and it will reject strings such as 1010. Now you guys can, now you may notice that in this A state, whenever input 1 is given, it loops back to the same state. But there's also another one. When 1 is given, it might also transition from state A to state B. So by this logic, this means that if I input 111, it might stay in the same state and it will never reach this final state of D. So I earlier said that 111 is an acceptable string by this NFA, and now I'm saying 111 might not be accepted. So that's the thing about NFA. So as long there is at least one path where this string might reach the final state, that string will be accepted by this NFA. So even there can be one or more paths where the string will not be accepted, where the string will not reach the final state. As long as there is another path where the string reaches the final state, that string will be accepted. So this situation can be applied to this string 111 as well. So one path for 111 is it might stay in the same state, it might loop over and over in the same state, and it will never reach this final state of D. But there is also another possible path, which is it will go through the states B, C, and eventually to D, again, which is the final state, making this 111 an acceptable string. Next slide, please. So Imasha mentioned earlier that whenever a null string is being input into the NFA, the states will be skipped without even reading the input. So that is what has happened in this situation. So when initial state A is being given the null input, null string, when a null string, it has transition from, it has straight down from A to E without even reading this input. Next slide, please. So another thing about NFS that Imasha mentioned earlier was that NFS can have 0 or multiple choices to transition into. So even in this diagram, you might also see there can be several transitions for the same input. So because of this reason, an NFA can have a set of possible states instead of having just one single state. Next slide, please. So I have already gone through these elements, which are states and inputs and so on. So I'm focusing on the transition function. So in here, so I'm taking one instance. So in here, in state A, when the input 0 is being given, when the input 0 is being given, it will stay in the same state. So when the input 1 is given, it can either stay in the same state or it can stay or it can transition to the next state. And when a null input is given, it will transition straight to the state E. So for inputs and the symbols that does not have any transitions in NFS, they can remain as empty sets. Next slide, please. So now that we have discussed what are DFAs and NFAs, we'll see what are the differences between these two. So in DFAs, for each input symbol, a state can transition from only one particular state to the next one. But in NFAs, for each input symbol, a state can transition into next multiple states. And for NFAs, I mentioned earlier, empty strings are being allowed. But for DFAs, empty strings transitions are not allowed. In DFAs, backtracking is allowed, but for NFAs, backtracking will not always be allowed. So for DFAs, when a string is accepted only if it is transferred to the final state. But in NFAs, as I told you guys before, a string is accepted if one of all possible transitions end in a final state. Next slide, please. Now Imasha will continue the rest of the presentation.
Now that we have discussed what are DFAs and NDFAs, let's briefly look into regular language. A language is a collection of appropriate string which is defined using an input set. Any that language that is recognized by some finite state machine is called a regular language. A language is not considered as a regular language when it is not recognized by any FSM. Other than that, if the said language requires memory, it will also not be recognized as a regular language since memory of FSM is very limited and it cannot store or count languages. The most important thing about the regular language is that any language recognized by a NFA can be used to construct a DFA that recognizes the same language. Next slide. Now we will move on to the topic of finite state machine with outputs. Next slide. FSM with outputs is an abstract machine, a finite number of states, a finite input alphabet, and most importantly, FSM with output is an abstract machine of finite number of states, a finite input alphabet, and most importantly, a finite output alphabet. Under this topic, we will discuss about Mealy machine and Moore machine. Please, next slide. First, let's talk about Mealy machine. Mealy machine was introduced by George M. Mealy, who presented this concept in 1955 in his paper, A Method for Synthesizing Sequential Circuits. This concept talks about a finite state machine whose output depends on the present state as well as the present input. Therefore, the output is represented with each input symbol for each is state separated by slash symbol. A simple Mealy machine can have one input and one output, while a complex one can have several inputs and outputs. Next slide. So, how do we describe Mealy machine? Unlike in DFS and NDFS, Mealy machines are described using a 6-element tuple. This tuple consisting of Q, which denote finite setup of state, sigma, which represent the input alphabet, or representing the output alphabet, lambda representing the output transition function, delta representing the input transition function, and q representing the initial state from where any input is processed. Next slide. Once again, Gihini will use an example to show how a solution to a problem can be built and used in Mealy machine.
Now we'll see how to design a Mealy machine that prints A whenever a sequence 0, 1 is being encountered in any input binary string. So do you guys notice any difference between the example that I've given now and the previous examples? So in our previous examples that are used for DFAs and NFAs, I wanted to see whether a certain input is being accepted by that system. But in here, I want to see what kind of output it produces when a certain input is being given. So in order to draw a Mealy machine, first we'll have to construct a DFA related to this Mealy machine. Next slide. So now you guys can see that I have already constructed a DFA for this example. So according to this DFA, it will reach the state 3, which I'll consider as the final state when this sequence 0, 1 is being encountered. So this means when this is the point. So the S3 is the point that output A should be printed, right? So in Mealy machines, both the present state as well as the input is being considered. So because of that, I'm going to represent my output along with this present state, which is S3, and with the input. Next slide. So you guys can see how I represented this output according to the present state and the input. And for the other transitions, I'll give my output as B. Next slide. Okay, so now you guys can clearly see how I've included the outputs along with these inputs and the present states for this Mealy machine. Now can we move on to the next slide? So by that diagram, we can identify the states of this diagram. So we have the states S1, S2, and S3, and we have the input 0 and 1, and we have the outputs A and B, and we have the starting state as S1. So this table represents both the input and output transition functions of the Mealy machine I have drawn before. So if I take an instance, if the present state of this diagram is S1, and I'm giving an input 0 is being given, it will transition to state 2. So according to this input 0 and the present state, which is S2, will be output B. Next slide. So now we'll see what kind of output will be produced to this binary number 1011. So for here, when I'm being given the input, when I'm being given the input 1, it is in the state 1, so the output should be B. And and then when and the next input is 0, so it will move to so it will move to state 1 and to state 2, And so now we have the present state as state 2 and the input as 0. So we'll have the output B. And then we have the next input, which is 1. So when 1 is given, it will transition from state 2 to state 3. So making the present state S3 and the input 1. So therefore the output would be A. And then for the last input, we have 1. So now this diagram is in state 3. And when the 1 is given, it will transition to state 1. So now our present state is state 1 and the input given is state 1 and the input given is 1. So the output that should be produced is B. So can you move on to the next slide, please, Sunisha? So now you guys can see that this is the output that is being produced when the binary number 1011 is being given. So now you can see how a Mealy machine can be constructed when according to a certain situation. Now we'll move on to the rest of the presentation.
Now we will move on to the Moore machine. Moore machine is a finite state machine which the output depends only the present state. Moore machine is named after Edward Moore, who presented this concept in his 1956 paper, Gedenken Experiments on Sequential Machine. In the Moore machine concept, there are no final states. Next slide, Unisha. Similar to Mealy machine, Moore machine also consists of a 6-element tuple. Like in the Mealy machine, the symbol Q denotes finite set of state. Then sigma denote finite set of symbols, input alphabet, or representing the output alphabet, delta representing the input transition function, lambda representing the output transition function, and Q naught representing the input state from where any input is processed. Now let's see how the concept of Moore machine is used when building a solution to a certain problem.
So now we'll take the previous example as before, which is to print A whenever the sequence 0, 1 is encountered in any input binary string. So now, unlike the previous example, now we are designing a Moore machine for this problem. So now you guys can see that I have already taken the DFA that I have previously used. So in Moore machines, it is important to consider in Moore machines only considers only the present state of the system. So this means that when in S3 is this state, that A should be printed because 0, 1 is encountered when it reaches the state of S3. So I'm representing this output I'm printing along with this state. Next slide. So this is how I'm representing my outputs along with the present state. And for the rest of the states and the rest of the outputs, I'm giving B, and they will be represented along with the other states. Next slide. This is how the other states will be represented. Now let's move on to the next slide. So now we'll see the elements of this Moore machine. So we have the starting state as S1, S2, and we have the states as S1, S2, and S3, and we have the inputs as 0 and 1, and we have the outputs as A and B, and then we have the starting state as S1. So this table that I have given below once again represents both the input functions as well as the output functions. So if I take one instance, let's take this let's take our present state as S1, and the output relevant to it should be output B, no matter whatever the input is. So let's move on to the next slide. So now, once again, we'll take the previous example, which is binary number 1011, and see what kind of output it will produce according to the Moore machine. So now we have a initial state as S1. So even before giving an input, an output will be produced, because in Moore machines, as I said earlier, only present states are being considered. So the output for initial, which is S1, should be B. And then we have our first input, which is 1. So when 1 is being given, it loops back to the same state, which is S1, so that our output will be B. And then we have the next input 0. So when 0 is being given, it will transition to state 2. So the present state will be state 2, and the output relevant to it will be B. And then when 1 is being given as the input, it will transition from state 2 to state 3. So now we have the present state as S3. So the output relevant to it will be A. And then we have, and then for the last digit, we have 1. So when 1 is given, it is being transitioned back to S1. So the output relevant to S1 will be B. So can you move on to the next slide, Manisha? So now you guys can see that this is the output that is being produced by 1011 in a Moore machine. Now let's move on to the next slide to see what are the differences between Mealy machine and Moore machine. So in a Mealy machine, output depends both on the present state as well as the present input. But for Moore machines, output depends only on the present state. And in Mealy machines, they react much faster to input since they react in the same clock cycle. But for Moore machines, they react much slower since they react one clock cycle later. And in Mealy machine, it requires very little hardware for designing, but for Moore machines, they require more hardware for designing. Now, Imasha will continue with the rest of the presentation.
Now, guys, you
Excuse
have
me.
an idea.
Yeah. Excuse me, dear. Shall we go for a simple question? I will share the question in the chat and I will give 2 minutes to you people to answer. It's a very simple question related to Moore machine. I have shared it in the chat. I will give 2 minutes to answer. There are 30 minutes, sorry, 30 seconds more. Right. Please complete your submissions, guys, quickly. All right. Thank you. Yes, we can continue the presentation. Sorry for the disturbance. I'm always disturbing. Sorry.
Now you have an idea about the types of finite state machine and how each type works. We will discuss some of the limitations of FSM. Earlier, Unisha mentioned that FSM is the simplest model of computation. While its simplicity is one of its major benefits, it also becomes one of their disadvantages. As stated in its name, finite state machine can only have a finite number of states. It cannot model a system which has undefined amount of states. This means that FSM cannot be used to produce infinite sequences. Other than that, FSM cannot multiply to arbitrary large binary numbers. Because of this reason, FSM model is not suitable for modeling every system. Can we move to the next slide? Let's see how finite state machine is implemented in hardware application. To implement a FSM in digital circuits, it is required to have a register to store state variables, a block of combinational logic that determines the state transition, and a second block of combinational logic that determines the output of an FSM. Charles L. Richard developed the Richard controller for this purpose. The Richard controller allowed for an easier design of complex finite state machine, and it also made it easier to implement finite state machine with hundreds or even thousands of states. Now, Unisha will explain how the concept of finite state machine are applied into the real world.
As Himansha said earlier, let's look into some of the real-world applications of FSM. The concept of FSM can be seen in many devices in the world. According to the concept, these devices perform a predetermined sequence of actions based on the sequence of events which are given to them as inputs. Earlier, I mentioned that elevators, traffic lights, vending machines use the concept of FSM. Now let's look into an example. Let's take elevators as the example. So we all know what elevators are. The sequence of stops is determined by the floors requested by the rider. So when you get into an elevator, you select the floor you want to go. Then once you select, the elevator will only stop in the floors selected by you. So please notice the floors selected by the rider and the floors passed by them in the next video.
We can see only a green screen. Is that only for me? All right.
So others didn't see the video? Guys? So I'll move into the next slide. So another example is traffic lights. Traffic lights changes the sequence when cars are waiting. So when we take traffic lights, there are three colors: red, amber, and green. So red says you to stop, and yellow says you to wait, and green asks you to go. So we can consider these three colors as states, and there is some sort of a transition in between these colors. So this short video clip shows that. Okay. So real world application of finite state machine. So in addition to the examples I talked in the previous slides, the FSM concept is used in electrical engineering field, linguistics, computer science, philosophy, biology, mathematics, video game programming, and logic field. So it is used in various fields. So other than that, in the computer science area, to modeling for the modeling of application behavior, design of hardware digital systems, software engineering, compilers, network protocols, and computational linguistics, this FSM concept is used. So now that we have come to the end of our presentation, let's review some of the facts we learned during the presentation. So we talked about what is FSM, and the graphical representation of FSM, the state transition diagrams, then the state transition tables, the types of FSM, DFA, NDFA, Mealy machine and Moore machine, and limitations of FSM, the implementations and real world application of FSM. So any questions? Okay, so I consider it as a no. And thank you very much for listening to our presentation. And this was our team. I hope you understand, and thank you once again.
Thank you, sir.
Thank you. Any other presenters ready to present today?
Yes, sir.
Yep, we go ahead then. Guys, are you people tired? Do you want a small break, or shall we continue? I think since it's online, you can stay in a bed and listen the stuff. So I don't think so. You want a break? So we continue, right? Okay. Yeah, continue to the next presenter.
So can you give me the permission to share the screen?
I have given. Right, you can go ahead.
Good evening, guys. So I know
We'll
it's
go to a full screen mode. Right, great. Go ahead.
good evening, guys. So I think it's a little bit tired for listening to 3 group presentations, but give us a little bit time since it's a last group presentation for today. So today, me and my group members are here to talk about logic gates and digital circuits. And I think comparing to other presentations, this is a easy topic. Today, we are going to give you an introduction about logic gates. What are basic logic gates?
Excuse me. Yeah, excuse me. Sorry for the disturbance. Again, I'm disturbing. Yeah, right. Guys, this is very important topic. You will be questioned in your final examination. Complete one question, usually complete one question, 30% around allocated for this topic. I mean, the logic gates plus the stuff that the students are going to present. So very important, not like the finance data or automata. This is very important. So you should be keep very interested on these subjects, these topics, because your final examination is question from this topic. All right. Yes, sorry, you can continue.
Excuse me, sir. Sorry to interrupt, sir. So
Yeah.
since it's like a important topic, as you said right now, can we have like a 10 minutes break at least so everyone would be refreshed by the time they come
Sure.
back?
Sure,
Is it
sure.
okay?
No worries. No worries. Presenters, it's okay.
Yeah. All right. Okay. Thank you,
Okay,
sir.
then we'll take a small break around 12 minutes. 4 o'clock, we'll back to the seats.
All right, sir. Sure.
All
Thank
right. All right, I think we can start the presentation. Sanjana, I think presenters.
Yes, sir. Yeah. Okay.
We'll continue.
Yeah.
Presenters, are you there?
Yes, sir.
Great. We'll start the presentation. Especially the people who do not done IT as a subject for the A levels, please make sure to go through this topic. Couple of students from the presentation group, 2 students, right, from IT background. I'm correct, isn't it? Yes. So they have good understanding. They have good knowledge in all the digital circuitries and stuff. So they can give a very wise knowledge for you. So you can continue.
Okay. Today we are going to talk about logic gates and digital circuits. First of all, we are giving you an introduction to logic gates, and after that, we are telling you what are the basic logic gates and the uses of these logic gates, and what are these universal gates. And also, we are giving you an introduction to digital circuits and what are these Carnot maps. And finally, we are telling you the uses of logic circuits. What is a logic gate? Firstly, before I give you a direct definition for this, I would like to give you the background of this definition. Inside our computers are billions of units called transistors. These transistors serve a variety of purpose, but they commonly act as a sort of very small light switch. Each switch can be turned on or turned off. Computer scientists will often represent a switch that is turned on from number 1 and the switch which is turned off as number 0. These ones and zeros form a number system called binary number system, and it is the fundamental language of computers. From just these zeros and ones, we end up with computers that can perform calculations, create documents, view images, browse the web, and more. How does this happen? In this series, we'll explore the foundations of computer logic starting from the fundamentals and building our way to more and more sophisticated systems. Using these features, our computers can store information. Each switch can store a single bit of information, a 0 or a 1. But computers don't just store information. They process it, transferring inputs into outputs. That's where logic gates comes. And here is a definition for the logic gate. Logic gate is the building blocks of computer circuits. They accept inputs and produce outputs according to the set of logical rules. Before we learn what are these logic gates, we should know about the history of these logic gates. The binary number system was refined by Gottfried Leibniz, and also in 1975 he proposed the concept of combined arithmetic and logical principles using binary number system. Later in 1854, George Boole discovered the concept of Boolean algebra. Later in 1886, Charles Peirce described the concept of logical operation in the electrical switching circuit. And in 1954, Walter Booth got the Nobel Prize in the field of physics for the innovation of the first modern electronic AND gate in the year 1924. From that up to now, still, researchers and analyzers prevail for the development of these molecular logic gates. The importance of logic gates. Why we are using these logic gates? We need these logic gates to make decisions. If we only apply this correct logic sequence only, our electronic outputs can be turned on. If not, it is turned off. Now we'll learn about the basic logic gates. There are 3 main basic logic gates: AND gate, OR gate, and the NOT gate. AND gate. AND gate is a logic gate that have two inputs and the output is on if the both inputs are present. And here y'all can see the symbol of the AND gate, and here is a circuit that y'all can understand the AND gate. In here, if both A switch and B switch both are on, this lamp will be on. But in the A switch is on, but the B switch is off, the lamp is off. And in the A switch is off, but the B switch is on, still the lamp is on. And when the A and B both are off, definitely the lamp is off. The second basic logic gate, OR gate. This is also a logic gate that have two inputs and that provides inclusive disjunction. And here is a symbol for the OR gate. And here is the circuit for the OR gate. In here, when the both A switch and B switch both are on, the lamp will definitely on. And in here, when the A switch is on and the B switch is off, but still the lamp is on. As same as previous, when the A switch is off but the B switch is on, the lamp is on. When the both are off, definitely the lamp is off. The last basic logic gate, NOT gate. Here, there's only one input and we are taking the complement of this input. And here the symbol of the NOT gate. In here, when the A switch is on, if we're taking the complement in this NOT gate, the lamp is off. And the switch, when the switch is off, if we're taking the complement of it, the lamp is on. So now, let's check your knowledge on the basic logic gates.
Thank you, Senali. Let's do a question based on these three basic logic gates. Here the question is, a cupboard has 3 locks and it has 3 keys separately. The L1 key is belong to the manager, L2 keys belong to the assistant manager, and L3 keys belong to the supervisor. Among these 3 keys, we must need the L1 key to unlock the cupboard, and one of the L2 and L3 keys is required. The question asks from us, what are the logic gates needed to solve this problem? So guys, you have any idea about to solve this problem? Okay, when we try to solve this problem, we must concentrate. We must give a very concentrate look on the question. In here, it says one of the L2 and L3 keys is required. In earlier, Senali said that in an OR gate, we need one gate. In OR gate, we must need one input. So in here they say one of the L2 and L3 keys required. It say we must need L2 and L3. We don't need L2 and L3 keys. We only need one of these 2 keys. So we can use the OR gate to solve this part. And in the upper part, it says that we must need L1 key to unlock the cupboard. It says that L1 keys must need for us. So next slide, please. In here, we can see L2 and L3 keys are going through a OR gate, and its output connects to a L1 out. It outputs connect to the L1 input. So we can solve this problem by using AND gate and the OR gate. Now Senali will explain what are the universal gates. Senali.
Okay. Here are more universal gates. There are 2 main universal gates, NAND gate and the NOR gate. In here, NAND gate is a combination of AND gate and the NOT gate. And here the symbol of AND gate and here the symbol of NOT gate. Combining these 2 symbols, here is the symbol of NAND gate. In this NAND gate, if we have 2 switches, both switches are on. If we go through the AND gate, it's on. But when we go through the NOT gate, we are taking the complement, so it's off. And the NAND gate, the result is off. When it is come to the next one, when the switch, A switch is on and the B switch is off, when you go through the AND gate, it's still off, but when we go through the NOT gate, it's on. Same as previous, when the A switch is off and the B switch is on, when you go through the AND gate, it's off, but when you are taking the complement of it, it's on, and the NAND gate, the result is on. And when both switches are off, when you go through the AND gate, it's off. And when you go through the NOT gate, you are taking the complement of it, so the result is on. Okay, now let's talk about the NOR gate. NOR gate is also a combination of OR gate and the NOT gate. And here is the symbol of OR gate and here is the symbol of NOT gate. Combining these two symbols, here is the symbol of NOR gate. In NOR gate also, when the A switch is on and the B switch is on, in the OR gate, this lamp is on. But when you go through the NOT gate, you are taking the complement, so it's off, and the result of the NOR gate, it's off. And in the A switch, when it is on and the B switch is off, when you go through the OR gate, it's on, and when you go through the NOT gate, you are taking the complement of it, then the result is off. When it is come to the A switch, again, as previous, when the A switch is off and the B switch is on, when you go through the OR gate, it's on, but when you go through the NOT gate, it becomes off because of the complement, and when you go through the NOR gate, the result is off. And when A switch and B switch both are off, and when you go through the OR gate, it's definitely off. And when you go through the NOT gate, you all are taking the complement of it, then the NOR gate is on. So now I would like to invite Dinusha to do the users of these logic gates.
Can you guys see the screen?
Yeah, we can see the screen, but not in a full screen mode.
Okay, so thank you. Now let's take a look on how basic logic gates are made from these universal gates. Basic logic gates by NAND gate. In here, simply
Excuse me, if you can full screen it. Nice, good. Go ahead.
Now correct, sir?
Yes, now it's okay.
Okay, basic logic gates by NAND gate. In here, I simply explain how these structures are made. So we can make a NOT gate using the NAND gate. In here, it's simple. We just want to connect both inputs together, and it gives the output as the NOT gate. We can make AND gate using NAND gates like this. In here, we must connect the NOT gate which we made using NAND gate used to the output of AND gate. In earlier, Senali said that the NAND gate is the inverse of AND gate. So when we connect the NAND gate to the NOT gate, it again made the AND gate. So after it, we can make OR gates also by these NAND gates. We can make it like this, where the two inputs of NOT gates are acts as the input of the NAND gate in here, and it helps to make us the OR gate. Basic logic gates by NOR gate. In here, as the earlier, we can make the OR gate by NOR gate using connecting both inputs together, and it makes the OR gate. And in here, we can make the OR gate by NOR gate like previously. We can connect the NOT gate which made from NOR gate to the NOR gate, and it gives us the inverse of the NOR gate, and we can get the OR gate. Likewise, we can make AND gate using NOR gates like this. We must connect to two outputs of the NOR gates to the NOT gate which we made from the NOR gate, and it gives us the AND gate. In here, why we are using these universal gates instead of other gates? We can make any other gates from the universal gates. So when we are making a circuit, it helps to reduce the complexity of the circuit. When we made a circuit from one type of logic circuits, it is very simple to identify the manufacturer or the user. So, and when we are using the universal gates has often very low number of transistors, and it makes the circuit as very efficient and very fast. And here, then XOR gate and XNOR gate. XOR gate and XNOR gates are the digital logic gates which we are using to make electronic circuits. In here, XOR gate is also known as the exclusive OR gate. The XOR gate give the logical output 1 when the both inputs are different. As we can see in the table, the input of A is 0, the input of B is 0. So the two inputs are same. Therefore, the output is 0. In the second line, the input of A is 0 and the input of B is 1. So the two inputs are different. So therefore, the output of XOR gate is 1. Now let's move on to the XNOR gate. XNOR exclusive NOR gate is based on NOR gate. In here, it produces the logical output 1. The two inputs are same. When we looking at this table, the input of A is 0, input of B is 0. So the two inputs are same. Therefore, the XNOR gate's output is 1. And second line, the input of A is 0, input of B is 1. So the output of the XNOR gate is 0 because the two inputs are different. We use these XNOR and XOR gates in digital circuits to encode data, decode data, and do digital encryptions. And this is the last part of the logic gates and applications of logic gates. We can use logic gates in digital electronics to do mathematical operations, to do control flow of data, likewise, and computer processing. We use logic gates in computer processing to do arithmetic operations and storage to make storage operations. And also we can use logic gates in security system, like we can use sensors by logic. We can make sensors by logic gates, and we can use access. We can make access controls by logic gates, and otherwise we can make consumer electronic. We can use logic gates in consumer electronics and industrial automations. Now, Keshini will explain what are digital circuits and what are the uses of it.
Screen. Okay. Now I'm going to do the part of digital circuits. Do you guys know about what is a digital circuit? Or do you have any idea about what it is? Some of you guys may have a small kind of idea about digital circuits because there are so many students who have done their who have done A levels for ICT. Okay, no one. Then I'll explain what is a digital circuit. Before we talking about what is a digital circuits, we should have to know what is about digital signal, because these digital signals are the digital signals are mainly dealing with these digital circuits. And also when we talk about digital signals are electrical signals that can have only two states. It means it have only two states. It means it has ones and zeros, or we can call it has only two states like ones and zeros, or it has two states like high and low. Likewise, then digital circuits. So digital circuits are designed to process these digital signals. And also, I would like to talk about what are the uses of digital circuits in my future slides. Then here in my slide, you can see there are two diagrams presented here. The first one is actually digital circuits can be divided into two parts: combinational logic circuits and sequential logic circuits. The first one is called as combinational logic circuits, and this one is called as the sequential logic circuits. But I'm going to do only about the combinational logic circuit part, and the Dinusha will explain you about sequential logic circuits. So here are the two block diagrams which we can use to make these sequential logic circuits and the combinational logic circuits. So what is meant by a combinational logic circuit? Combinational logic circuit is a type of digital circuit that produces an output based solely on the current input values. It means combination logic circuits cannot have doesn't have any memorable element. It means it always gives the output according to the current input. When we talk about sequential logic circuits, it always gives the output according to the previous outputs. But in here, combination logic circuits, it always gives the output according to the current input. That is why it hasn't any memorable element to keep it there in the to keep the current values in the memory. So this is the block diagram of the combination logic circuits. Here you can see that we have entered A, B, C, D as the inputs, and we have got X and Y as the outputs. So in a combination logic circuit, we can have more than one outputs as the output. And also this is an example for a combination logic circuit. Combination logic circuits are always made up by can be made up using different basic logic gates. So here this is an AND gate, and this is a NOR gate, and this is an AND gate. By looking at that, we can see that the combination logic circuit has made up by using three different kind of logic gates. Likewise, we can make those combination logic circuits by combining these types of circuits, these type of logic gates. So the uses of the combination logic circuit are, we can use these combination logic circuits for the functions like arithmetic and logic functions, for the functions like data transmission, and for the functions like code converters. Okay. Now I'm going to talk about a very important part of these combination logic circuits, the laws using combination logic circuits. I'm going to talk about five main laws. Those are commutative law, associative law, identity law, distributive law, and De Morgan's law. Commutative law can be presented in two ways, like commutative law of addition and commutative law of multiplication. I would like to give you this by using an Excel sheet. Then you can gain a good idea about that. So, commutative law of addition. Here I have used two inputs as A and B, and also I have used two inputs like A and B. These zeros and ones are the number of ways which I can use which I can present these zeros and ones. Here actually we can get this. If there are two inputs, we have to get the power of 2 to the power 1, and if there are 3 2 to the power 2, if there are 3 inputs, we can get the number of ways like 2 to the power 3. Likewise, always the power of the power of the 2 will be the number of inputs we should have, number of ways we should have to get as the inputs. So here A and commutative, when we talk about commutative law of addition, A and B gives zeros and zeros. Sorry, A equals to 0, 0 and 1, 1, B equals to 0, 1, 0, 1. You guys can remember that Senali had explained you about OR gate, NAND gates and NOT gates. Likewise, the A plus B is the OR gate. A plus B means the OR gate. It means whenever if any input is equals to 1, then the output always should have to be equals to 1. If any input is equals to 1, then the output is 1. So in here, in the first one, 0, 0 means there are no ones here. So the output is 0. And 0, 1, the B is 1. So the output is 1. In here, A equals to 1 and B equals to 0. So the output is 1. In here, both inputs are 1. So the output is 1. And also, the commutative law of addition means A plus B equals to B plus A. That's why I have taken A plus B and B plus A as separate cells. B plus A means now we are going to get the value output for the B plus A. First we have to look for the B's values, and the second we have to look for the A's value. So B is equal to 0 and A equal to 0, then the output is 0. And B equals to 1, A equal to 0, then the output is 1, because the only one input is equals to 1. And the B is equals to 0, A equals to 1, then the output is 1. Here the both inputs are 1s, definitely the output will be 1. So you can see now how this law has been correct, because A plus B, the values gained for A plus B will be are definitely equal to the values gained for the B plus A. Likewise, when we talk about the commutative law of multiplication, AB and A into B should have to be equal to the B into A. So A into B means 0 into 0, 0, 0, 1 into 0 into 1, 1, sorry, 0, 1 into 0, 0, 1 into 1, 1. Likewise, we can apply. And the next one is B should have to multiply by A. So B into 0 into 1, 0 into 0, 0, 1 into 0, 0, 0 into 1, 0, and 1 into 1, 1. In this also you can see that both the outputs of AB will be have been equal to the outputs of BA. So this is how the first law of, it means the commutative law, has been made. Then we are talking about the associative law. Associative law also have two different associative law also can gain in two different ways. Associative law of addition, associative law of multiplication. Here the A plus B plus C equals A plus B plus C. As I told you earlier, if we have three inputs, the number of ways zeros and ones are number of ways that we can gain zeros and ones are 2 to the power 3. So that's why I have taken 1, 2, 3, 4, 5, 6, 7, 8 like that. I have gained 8 number of ways zeros and ones can be presented. So the law is A plus B plus C equals to A plus B plus C. When we going to do this? So A plus B, I have gained the value for the A plus B's and I have the values for C's. So I can A plus B plus C means, you know that if any value of the input is equals to 1, the output should have to be 1. So 0, 0 equals 0. 1 plus 0 equals 1 because only one input is equals to 0. So the output will be 0. 0, 1 into 1. 1, 1 equals 1. 0, 1 equals 1. 1, 1, 1. 0, 1, 1. 1, 1, 1. Like that. Then we have gained the values for the A plus B plus C. Then we have to take the values for the B plus C plus A. So I have taken the values for the B plus C. Sorry. So 0 into 0, 0 plus 0, 0. 0 plus 1, 1. Only one value is equals to 0. 1. Then the output will be 0, 1. 0, 1, 0, 1, 1. 0, 1, 1. Again like that. 1, 1. Like that. So you can see that the outputs of the A plus B plus C have been equal to the outputs of the B plus C plus A. This is the associative law of addition. Now we can move to the part of associative law of multiplication. Here also we use the same method, AB into C and BC into A. I will fill by my own. Here A into B has gone through an AND gate. It means both the inputs mean both the inputs of input of C and input of AB should have, both the inputs should have to get 1. Then if the both inputs are equals to 1, then the output will be 1. Otherwise the output will be 0. So in this case, only both outputs are equals to 1. In other cases, both inputs are different from each other. Like that. Then the BC into A. So BC inputs of the BCs and inputs of the A's, both inputs should have to equal to 1. Otherwise the outputs, then only the output will be 1. Otherwise the output will be 0. In here also 1 and 1 in the last cell. So I put 1 here. 0, 0, 0. So now you can see that the output of AB into C has been equal to the outputs of BC into A. So this is the associative law. Then I'm talking about the identity law. Identity law also has these, also can be presented in 2 ways, like identity law of addition and identity law of multiplication. Identity law of addition. Here I have used only one input as my input. So the number of ways the zeros and ones are can be implemented is 2 to the power 1. It means 2 ways. Only 2 ways can be implemented. Identity law of addition. Identity law of addition here, a plus 0 should have to be equal to the value of a. So a plus 0 means a plus 0 means if any input is equals to 1, then the output should have to equal to 1. So 0 into 0, 0. A equals to 1, then the output will be 1. Likewise, so you can see that a had been equal to the values of a plus 0. You can see how these laws are correct. And the identity law of multiplication, in here, identity law when we are talking about identity law of multiplication, a into 1 should have to be equal to the values of a. So a into 1 means 0 into 1, 0, 1 into 1, 0, 1. Then you can see a into 1 had been equal to the values of a's. So like that, we can say the identity law. Then distributive law. Distributive law can be gained as a into within the brackets b plus c equals to the a into b plus a into c. In mathematics also we have used this method to solve problems. It means we have to multiply a by these two values. We have to multiply a by b and a by c. That's how we have taken a into b plus a into c. So this is the here also I have used 3 inputs. So the number of ways can be implemented is 8 ways, like that. So I have gained the functions like a, b, c, b plus c. Here we have b plus c, a. That's why the output has b plus the output a into b plus c has taken by multiplying a values by b plus c values. So b into 0 into 0, 0, 0 into 1, 0, 0 into 1, 0, 0 into 1, 0, 1 into 0, 0, 1 into 1, 1, 1 into 1, 1. Likewise, I have taken the values for the a into b plus c. And the values for the a into b plus a into c, I have separately taken these two values to the two different cells. A into b, 0 into 0, 0, 0 into 0, 0, 0 into 1, 0. Likewise, I have taken the values for a into b. And also I have taken values for a into c, like a into 0 into 0, 0, 0 into 1, 0. Likewise. Then to prove that this law is correct, I have to put these outputs. I have to put these two values by using a OR gate. So a into b and a plus c are gone through a OR gate. It means if any value of the output is equals to 1, then the output should have to be 1. So here 0, 0, 0, 1, 0. I have to look at only these through parts. 1, 1 and 1. So now you can see the outputs of a into b plus c has been equal to the a into b plus a into c. The next and the last one is the De Morgan's law. So the De Morgan's law means the complement of a product is equal to the sum of the complement. here you can see that A into B's complement has been equal to the A's complement plus B. The sign has been changed. Here we have an AND gate, but when it comes to there, it has become to a OR gate. And also in here also, A plus B's complement has been equal to the A's complement into B's complement. It means in here we have a OR gate. By when it comes to here, it has a AND gate. So De Morgan's law also can be presented by like this. We have to take the values for A's and have to take the values for B's. Then we have to take the values for A's complement. It means the complement of A. If it is 0, then the complement is 1. If it is 1, then the complement is 0. Likewise, we have to take two separate cells for A's complement and B's complement. Then sorry, I have to add another. Now I can get. So A's complement, A into B, I have taken the values for A into B like 0, 0, 0, 1. So the complement of A into B's complement of the A into B is equal to 1 and 0. So here you can say in De Morgan's law, here A into B's complement should have to be equal to the A's complement plus B's complement. So A into B's complement means A into B's complement means 1, 1, 1 and 0. So then the next one we are asking is A's complement into B's complement. So we have to go A's complement plus B's complement. It means we have to go A's complement and B's complement through a OR gate. Then if any value is equals to 1, then the output is 1. If the both values are equals to 0, then the output will be 0. Likewise, we have gained the values for A into B's complement and the A's complement plus B's complement. So you can see that A into B's complement had been equal to the A's complement plus B's complement. So this is the way, so these are the laws which we have to talk about. Okay, now I would like to invite Dinusha to present about Karnaugh maps.
Thank you, Keshini. What is a Karnaugh map? A Karnaugh map is a graphical method used in digital logic design to simplify a Boolean algebraic expression. In here, it is a two-dimensional grid of cells where each cell represents a possible combination of input value for a Boolean function. When we talk about history of Karnaugh maps, a person named Maurice Karnaugh introduced Karnaugh maps in 1950. He introduced this to get the minimal answer for a Boolean algebraic function. And this is the structure of a Karnaugh map. And when we talk about how the Karnaugh maps are made, the number of cells, cell means this square, the number of cells are determined by the number of inputs. Like then we have 2 inputs. It means 2 to the power 2. Then we need to draw 4 cells. And when we input 3, like when we input 3, like A, B, C, we need to draw 8 cells like this. And like this, when we input 4 values, A, B, C, like A, B, C, D, we need to draw 16 cells. When we solving problems using Karnaugh maps, there are several. We need to follow several rules. In here, I'll explain these rules one by one. Groups may include 1. We can't group the cells which include 0. In here we have 0 and 1, so we can't group it because it contains a 0. In here we have 2 1s, so we can group it because the both cells are 1. In here, the second rule: groups may be horizontal or vertical, but not diagonal. Then we can see in here the groups, this group is vertical and this group is horizontal, so we can group these 3 cells, and in here these 2 cells are diagonal, so we can't group these two ones. The next rule: groups must contain 1, 2, 4, 8. Likewise, in here we can group these cells by power of 2s. We can group, this group has 2 cells, so 2 is the power of 2, and in this group has 3 cells, so 3 is not a power of 2. So we can't group these 3 cells. In here we have 4 cells with 1, so 4 is the power of 2, so we can group this. And in here we can't group because 3 zeros are here, and we can't group this like 8 group, but we can group these 1 4s, and we can't group like this like 8. And we can see this groups has a number of cells which are not the power of 2, so we can't group this like this. This is 3 and this is 5. They are not the power of 2. Then each group should be as large as possible. It means we have 1, 2, 3, 4, 5, 6 ones. We can group this by 2. We can group this like this. We can group this by 2 ones, 2 ones, 2 ones. But in here we can group these 4 ones together as one group. So we must group the cells as large as possible. In here we can't group like this because we can group these 4 cells together, and we can't group like these 2s. And in here, when we have no groups, when cell which has the 1, we can't group because there are no ones here, so we can group this 1 alone, and with these 2 ones as one group, these 2s and 1s as one group. In this, groups may be overlapping. Groups may be overlapping means we can wrap this group. We have this is one group and this is one group, and there we can overlap these groups. In here they grouped as one, two of ones, two of one, two of ones. Then we do like this. We break the rule. The groups must as large as possible. So we can do the groups like this by overlapping the other groups. Now Senali will explain what is sequential logic circuits and what are the uses of it.
A sequential logic circuit refers to a special type of circuit. It consists of a series of various inputs and outputs. Here, the outputs depends on a combination of both.
Senali, you are muted. Please turn on the microphone.
Can you hear me now?
Yeah, we can hear you.
A sequential circuit refers to a special type of circuit. It consists of a series of various inputs and outputs. Here, the outputs depends on a combination of both the present inputs as well as the previous outputs. This previous outputs gets treated in front of the present state. Thus, the sequential circuits consist of the combinational circuit along with its memory storage elements. It doesn't need to consist a combinational circuit all the time. A sequential circuit can be basically contain only the memory element. Dinusha, can I have the next slide, please? And here is the block diagram that which I described before. Next slide. And here is the difference between combinational logic circuits and sequential logic circuits. In combinational logic circuits, the output depends only upon the present inputs. But in sequential logic gates, it depends on the present as well as the past input. In combinational logic circuits, elementary building blocks are the logic gates. But in sequential logic circuits, it's flip-flops. And in combinational logic circuits, don't have clocks. They don't require triggering. But in sequential logic circuits, they are dependent on clocks and they need triggering. And in combinational logic circuits, they use arithmetic used for arithmetic as well as Boolean operations. But in sequential logic circuits, they mainly use for storing data. So guys, our presentation is over. If y'all have any doubts, y'all can answer.
You have questions, you can answer.
Ask. Sorry.
All right, guys, any questions? If you have any questions, you can ask. All right, it seems no questions. Thanks. It's a good presentation, clear and very nice space is gone. Right, so we'll meet next week then in online mode again. So the students who are planning to do the presentation, please ready and come. So we'll do the presentations online mode until the things are back. Make sure to send your PowerPoint presentations to me, then I can upload into the course page, probably today itself. Send it, then I can finalize this update in the course page. Then my work is almost done, so I can move very smooth manner. Ashan and the other one, I can't remember the name. Shah, who is that? Sahan now something.
Sanjana.
Sanjana. Right, Sanjana. Please make sure to let the colleagues to push to send all the PowerPoints to me today itself. Then I can upload and finalize this work, as well as Ashan. I think the recordings are with you. So next week or some like after next week, we'll finalize that recordings also. We'll upload into this course page. Then we'll finalize the work. Yeah, questions. Yeah, Mihan, it's a
We'll
question.
have some individual presentations as well, 5-minute ones.
Yes, we'll do it next week or after that. Probably I have given the full authority you to decide when to do the presentations. So
We
that
planned on doing them today, sir.
today. Okay, how about the idea about the others? Do you want to hang on today to do the presentations?
Excuse me, sir. The one thing is that people seem to be really exhausted now. I don't think whether it will be worthwhile if the individual presentations are done right at the moment.
Okay.
If Mihan is okay, shall we have it next week or after that, Mihan? Is it okay with you?
Sure, sure, sure.
Yeah,
All right.
considering the people, their reactions.
All right. So next week or something like somewhere that free we can do, Mihan. Thanks for the interesting showing the interesting for the presentations. Good, appreciate a lot. And others, please go through with these materials. I have updated the course page as much as that I can. So you can go through some of external materials, some of the things I have properly arranged probably, right? Remove all the cluttered out things and clean out the site so you can go through very smoothly. And don't worry with the weeks and stuff because I have arranged according to the what we call this course curriculum. We have, as I told in the very first day, we have mainly few topics: Boolean logic, system architecture, basics of operating systems, and computing models. So these are the basic 4 things that we need to focus on this module under this module. So I have renamed these topics according to the weeks that available in the course page. So don't get upset with the schedule that you are doing the presentation and what is in the course page. Don't get upset. We do the usual presentations. I have just updated the schedule to make like a nice, elegant output, right? That's the ultimate objective, not to mess up you. And I have added the what we call this sum of topics, especially the operating systems, what you need to go through. And I have updated a book for system architecture. And what are the things that you system architecture or computing models? I can't remember. One I have added, and I'll upload some of additional materials also. If you are an advanced learner, I have given some advanced topics, advanced references for you to learn. That's very good if you can. If you are really hard, like you don't have very much sophisticated interest on this subject, no worries at all. Those are some advanced topics, not for a general or a normal student, but for an advanced student only. Right, so we have done a nice set of presentations today. Everyone done a good job, appreciated a lot. So your presentation skills are very good actually. Appreciated everyone's presentation skills. Some of you are presenting in a mode like not too fast. Everything is good. It's clear and detailed, and some of the topics are quite technical. So at a glance, sometimes you might be unable to understand. That's the usual situation. That's why I'm trying to upload all the videos earliest as possible. I'll upload this video tomorrow morning probably. And today I want to go out for a while, so I'll back tomorrow morning. So once I back, I'll update definitely the course page with today video. The rest of the things I'll upload once your representative is given all the videos to me. Then I'll upload everything. Then we'll finalize the site and the learning things that you need to learn. So actually, we are not expecting very technical things from you, but you have given very technical things. Very good, actually. That's outstanding. You're going out of the boundaries and you're thinking out of the box. That's very good. See this kind of undergraduates, which makes very interesting to teach. Right, so I know it's very good effort that you have given to present this kind of a big thing to this audience, and especially I don't feel anything difference that physical or online. It's nice presentation flow from the first presenter to the last presenter. Right, very good, guys. We'll meet online in next week then. Any questions furthermore? Any questions? No. Make sure to add your out time in the Google Sheet that I have shared. I'm going to remove access within 5 minutes. So add your details, your leaving time as 5 p.m. If you are here, so within 5 minutes, I'm going to remove the access from everyone. So it's your responsibility to update now itself. All right, then have a nice day and have a nice week. We'll meet next week online. See you. Bye-bye.
Thank you, sir. Bye.
Thank you, sir.
Thank you, sir.
Thank you, sir.
Thank you, sir. Thank you, sir.
Thank you, sir.